Welcome to installment 3 of programming a 6502 assembler in assembly language. The bird is chirping. So today what we're going to do is keep going with this file abstraction. And last time I worked mainly on getting the pointer, which is inline, extracting that from the code, and using the I basically created the create command. So here, if you want to create a code, you call this right here. It builds this command block and then jumps to iPointer, which extracts the pointer, which would be this pointer right here, from the code, and then goes ahead and creates the file as requested. Okay, so what I'm going to do right now is kind of build on this and work on these other things, these other calls that will also have this inline pointer. And the first is to delete a file, which ProDOS calls unlink. That's not it there. That's it here. ProDOS calls destroy, but in Unix it's called unlink. All right, I'll just call it unlink here for no good reason, just cause. All right, and you see it has a parameter count of 1, and the call is call hexadecimal C1. So all I need to do here is load a 1, store that in command block byte 0, right there. All right, and I think that's it, right? Then I'll just jump to iPointer. And iPointer will extract the path name and put it right here. It's in bytes 1 and 2, which is the same place it was in the create call. So that's all great. Okay. And then down here, what I have to do is, I get this parameter count right here. I've said if it's 7, that must be the create call, otherwise it goes to done. All right, so now I'm going to change that, and instead it's going to go to, I'll just call it iPointer 3. Okay. So that's create right here. And I'll just go ahead and compare that to 1. If it's not 1, I'll go down to done still. All right, otherwise I'll make the ProDOS call. And this is C3. Sorry, C1, my mistake. C1. Okay, so that's it. I don't know what this thing is. Oh, I see, that was supposed to go here. Okay, there we go. So to destroy a file, delete a file, C1 is destroy. Okay. Let us there. Okay, so what I did was I printed out this thing for create, the string that says create. Then I try to create the file, and then I go down here to handle the success or failure or whatever. And I can do the same thing here. So I'll just print out. Now unlink. And of course I'm going to unlink this same file that I just created right there. That is with the name my file right here. Okay, now actually what I'll do here, instead of branching down here to no errors, I'll just jump to result, or JSR to result. Okay, get rid of that. Here also JSR result. All right, and this will be result, which is just it's the same thing. It prints out whether the operation succeeded or not. If it succeeded, then it says success. If it doesn't succeed, it prints the error code and says failed. So that should work just fine. All right, and this RTS is just ending the test program here. So yeah, it would be nice if I could remember my own source file name. Okay. Oh, by the way, I went ahead and deleted the my file before. You see it's not there. And if this works, it will be created and then destroyed. So it still won't be there, but we'll see the results. Okay? Create error 0, unlink error 0. Probably, error 0 means there's no error. I mean, there's no 0 error code. Probably it actually succeeded, but there's just a little issue with the subroutine called result. So let's take a look at this. Oh, okay, of course, it's doing all this stuff, right? It's not actually checking the whether there was an error or not, right? So what I should do here is if carry is clear, go to no error, otherwise do this stuff here. Okay. Right, and it succeeded. Okay, so we have success and create, success and unlink, and of course the file isn't there because we just deleted it. Okay, so that was pretty quick and easy. The next one we're going to worry about is open. And if I go here, I'll have to find it down here somewhere. Did I skip it? Probably. Read. Open. There it is. Open. Okay. So it has a parameter count of 3, and it takes a path name and the same bytes 0 and 1 and 2 of the command block, and then it takes an IO buffer that is a pointer to some buffer that ProDOS can use to read the file. And and let's just say a real operating system, this buffer is allocated internally by the operating system, and you don't have to worry about it. But in ProDOS, we have to give it this buffer. And ProDOS also has some rules about how you mark pages of memory used or unused, and it has to be an unused page of memory. And then it will return to you, if it succeeds, a reference number, which is the file descriptor. It's just it will be the number that you use when you make read and write calls to refer to the file. Okay, but for right now, the important part is that we get this path name the same way we did for the create and destroy calls. Okay, so I can go here. We have create unlink, and I can make open. All right, and with open, what I'm going to have happen is that, first off, we'll go ahead and put the parameter count here. That's this right here. But when you call open, you should put the path name of the file you want to open inline, just like you did for create and destroy or delete or unlink, whatever you want to call it. But the IO buffer should be stored in X and Y. Like, you should load your pointer to the buffer that you want ProDOS to use in X and Y. I mean, we could also make that inline. Actually, I'd rather pass everything in registers usually. But anyway, I'll just use X and Y here for that. So when this open routine is called here, the pointer to the buffer is going to be in X and Y. The pointer to this IO buffer is going to be in X and Y. And so we just have to store those into the command block locate bytes 3 and 4. Okay. +4. And jump iPointer. Okay. So we've done this, we've done this. This will be done by iPointer, and then this is a return value. It's not something we give it, it's something that ProDOS gives back to us. So we have to go down here now. Okay. Here's where we'll look at, we're looking for a param count of 3 will mean open. And what is this is C8, okay. Open. RTS. Not quite, because what we want to do here is we want to go ahead and load. We want to return the reference number or the file descriptor, this thing here, in the A register. And that is at byte 5 of the command block right here, 5. So we'll load that and then return. Okay, well, that actually does mean that if there's an error, we should check for an error, because if there's an error, we won't get we're destroying the error code here. So I don't want to do that, actually. So I'll say if there's an error, okay, then just go down here. If there's not an error, go ahead and load in the file descriptor. So that means that will be absolutely necessary to check for error using the C bit, the carry bit, right? ProDOS kind of allows you to do it one of two ways. You can check for error by looking at the C bit. If the carry bit is set, there's an error. If the carry bit is clear, there's not an error. Or you can look at the A register, the accumulator. If it's 0, there's no error. If it's not 0, there's an error, and that whatever the contents of A are is the error code. But now I'm just saying if there is an error, we're going to just return, and the error code will be an A. Otherwise, if there's no error, we will load the file descriptor in A. So that means that the code which calls this, that is the code which calls the open function, must use the carry bit to check for an error, but that's fine. Okay, now as I said, this IO buffer that you give it is in a way special. It has to be an available free page of memory. Now, it's actually, ProDOS doesn't really keep track of this. Your own user program has to keep track of which pages are free or not, but it's supposed to set some bits in ProDOS's memory space that will allow ProDOS to know whether this is in use or not. Kind of the idea is that you could have multiple programs, like a program can install some piece of code somewhere up in high memory and set that bit as used, and then another program which runs should, before it tries to use that memory, check the bitmap and say, hey, is this thing being used or not? If it is being used, then I won't use it. Okay, that's kind of the idea. It's just a way to do, the idea is that programs which play nice with each other and follow all the conventions could have, like some program could run and leave something resident in memory that would, who knows, it could be an interrupt service routine or something of some sort, and other ProDOS programs would recognize that and respect it, not destroy that, not take over that memory. But anyway, for my purposes right now, I just need to make sure that that memory, or that I need to know that the memory I'm going to use for this IO buffer is marked free. And I checked earlier, and when it runs here, when this program runs under the Orca environment, the only memory pages that are set to being used are those occupied by the program itself. So when Orca loads the program into memory to run it, it marks the pages that this program uses in terms of, like, just for its code and data as used. The other pages are left free. So that means that what I can't do is I can't, for example, make here something like IO buff, and it needs 1 kilobyte. So I can't do this, because if I did this, that means that this is part of the image of my program. It's part of the binary file that's loaded, and it will be marked as used. I mean, yeah, okay, I could mark it unused. That's a possibility. But the easier thing for me at the moment is just to basically go to a place where I know that the memory is not marked as used, like up here near ProDOS, and just basically use that. So I'll say here, for example, IO buff is equal to, and I need 1 kilobyte of memory. So I'm going to count backwards 1 kilobyte from BFOO. That is EDCA, right? Is it BA? B, C, D, E. No, it's BB. All right. So this is 1 kilobyte from BB00 to BF00, or BBEFF is 1 kilobyte of space. And I know that this is not being used. I know it is marked free in ProDOS's memory usage bitmap. So this will work. Now, there is an argument to be made, I suppose, that this file IO abstraction code should take care of this and not require the colors of the code. That is, not require not require the code that's going to call the open. Right here I'm calling create, here I'm calling open. Not require this code to manage the buffer. Instead, I should have this code down here, which implements the create, the unlink, the open, and close. That should manage the buffers. There is an argument to be made about that. But I think for the moment, I'm not going to do that. I'm just going to, because this is file IO abstraction, but it's also just part of this assembler. I'm not trying to do it as a general purpose library. So what I will do, ultimately, the assembler will probably need to open about 4 files. So that will be, yeah, it'll have to have space for all those things. And here, let me just pull in my calculator. So BF00 minus 400 hexadecimal is 1 kilobyte. That's that. So that means I might have to go back to AF00, right? I might need, 4 kilobytes of space for these buffers. And to be honest, that's like a big hit. I mean, 4 kilobytes of space out of the limited amount we have available to us is a lot. But for the moment, I'm just going to use it. And then if it turns out to not be a problem, it's not a problem. Hooray. So I'll go ahead and set that to AF00. And, in the future, maybe I'll need to have, I might need more than this. I might need this would be B300, right? B700. And this is BB00. So I might need to use all of these buffers here. I might need to use all of these things. So I just set those up here for now. And yeah, later these might have to be made global equates so they can be seen everywhere in the program. I'm not quite sure. We'll see. Or I can just move them somewhere else if necessary. But right now we're just testing, so. All right. So this is the test code. Now to call open, I'm going to have to load X with one of these buffer addresses. And then just sort of open, and I have my inline file here. It's going to be the same file called my file. All right, okay, good. So it's kind of dumb to open the file after I destroy it, after I unlink it. So let me go ahead and do the kind of painful copy and paste here. Okay, so now what I'm going to do is I'm going to create the file, open it, and hope that works. And I'm going to then destroy the file. Before that, it's not going to let me destroy it without closing it first, I imagine. So let's just go ahead and quickly implement the close command as well. All right, and if I look here, if I can find the close command. Here it is, okay? For the close command, all I need is the reference number, right? So that's going to be a little bit different. I don't have to have, I don't need to extract anything. So I just say, this is parameter count of 1. Okay. So when you close, you're going to have, of course, when you close your file, you're going to have already the file descriptor in the accumulator. So I need to store that in +1, byte 1, right here. All right, and then I put 1 in as the parameter count. And I'm just going to do the JSR to MLI right here. And it is CC is is the command number. All right, and this is called cmdblk, I believe. That is right. Okay. So that, you see, doesn't jump to iPointer. It just does everything right here. All right, so I'm going to need here and this is just, for my debugging purposes, I'm going to print out these strings and say whether each thing was successful or not successful. Okay, so here I'm opening the file, and then now I will close the file. All right. I need some place to store the file descriptor. This will be fine. Just a byte to store the file descriptor there. So after I open it, I'm going to need to store whatever I have in the file descriptor. Now, of course, this could be an error code if it didn't work. If it did work, it's the file descriptor. I'm doing that before I actually go and print out the result. All right, I'll have to come back to that in just a second. All right, so now I need to get the file descriptor back and close, and then check the result. Okay, so what I'm going to do here, though, is I'm going to go ahead and, at this point, push the processor status register. Okay, and then here I'm going to get it back, and the reason for this is so that I can remember whether or not this open call succeeded or failed. So if it failed, I'm just going to, if it failed, I'm going to not try to close the file because there's no point closing if it opened. Instead, I'll just go straight to the unlink. Okay, which will be right here. Okay, so I try to open the file. I just remember the status of that, whether it succeeded or failed, by pushing the processor status flag. I then store the file descriptor, assuming it succeeded, otherwise I'm storing the error code. I jump to result, which will print out success or failure. I retrieve the processor status register, which will give me the carry flag back. If carry is set, that means there was an error with the open, and I'll just go ahead and delete the file. If error open succeeded, then I'll go ahead and close the file here. All right, I think that all looks good. Yeah, I made that same stupid mistake again. That's not even the file I want. This one. Yeah, see? Okay, good. Let's try it. Okay, create, open, close, unlink, all success. Yeah, I'm kind of trusting that it's true because there's no sign of the file here. There's my foo file, which was, for the copy and paste. But it also appears to succeed, so let's go back and look at this some more. All right, so we've taken care of the create, the destroy or unlink, the open and the close. So now we have to worry about read and write. Now, read and write is going to be very similar to the others with a one little wrinkle, and I'm going to start with write here. So write has a param count of 4, and then needs a reference number, which is the file descriptor, and then this data buffer, that is the pointer to the data buffer where from which the data to be written to the file comes, is here. And then there's going to be the number of bytes that you want to write, and then this will, the result of how many it actually wrote. Okay, I'm going to have this request count be stored in X and Y when you call the write subroutine, but this will be inline. But there's a small problem, which is that the inline, the I pointer routine, okay, the I pointer routine here, right? It stores the inline pointer that it retrieves in bytes 1 and 2. So I'm going to go ahead and use it because I want to reuse the code, but after it executes, I'm going to have to move these things up there. All right? So here we're going to have write. Okay, and X and Y are going to, is the request count that's going to be here. Okay. And I think I can go ahead and put them there. That's command block +4, command block +5. +5, okay. The reference number is going to be in A, but I can't put that here now because the I pointer routine is going to write it's going to extract a pointer from inline code and it's going to put it right here. So I can't do that. Instead, I'm going to have to put it somewhere else and then move it. And I guess I might as well put it here. I just put this reference number here for now and move it then afterwards. So put that in. This is the file descriptor. And this is the request count low. Request count high. Okay. Okay, and now I need to go ahead and jump to iPointer. Okay, and down here, okay, this is going to be looking for a param count of 4, which is going to be the same for both read and write. Read also has a param count of 4. And you know, all the parameters are the same. I'm just starting with write, but they're basically going to work the same way. Okay, and this is going to be here, iPointer 6. Okay, so at this point, when we get here, the data buffer, the pointer to the data buffer, which was inline, has been read in, but it's in these 2 bytes, 1 and 2, so I need to move them. Okay. +2. Okay, so I took what was in byte 2 and stored it in byte 3. I took what was in byte 1 and stored it in byte 2. So I took this and moved it here. I took this and moved it here. Now I need to move the file descriptor from here up there. Like that. So I originally put the file descriptor here. Now I've moved it up there. So at this point, I have this is correct, this is correct, this is correct, this is correct, and everything's good. So I can do here JSR MLI, and the commander is CB, hexadecimal CB. Well, let me hold off on that for a minute. Okay. Okay. So I'm going to, then this is going to be right. So that should be fine. Okay, I store the request count in 4 and 5, which is what I want. I store the file descriptor, or the reference number, in 6, only because the I pointer is going to write on top of this stuff here. So to store it there, just to get out of the way. Then I jump to I pointer, okay, which extracts the pointer and puts it here and here. All right, and then I move it. Move from 2 to 3 and from 1 to 2. Move this here and then this here. Now the pointer to the data buffer is in the correct place. Then I move that file descriptor I put in command block +6 back to the correct place, which is command block +1 here. Move from here to here. And now I can call write. I can actually make the right call, the WRITE, write call. Okay, now there is a small problem, and I also want to do read, and yet read has the exact same parameters, same parameter count, everything's the same. So how am I going to distinguish the two? Well, I don't really have to, do I? I can just, what I can do instead is, there's 2 ways I could do this, but I think it's kind of easiest just to put a little label here, RWCMD, okay. And actually, since I'm doing this, let me just go ahead and put a big fat 0 here. Okay. And what I'll do here is I'll say write, and I can store that in. So I'll take the CB, which is the command for write, and I'll store that in this byte down here, RWCMD, here. So that means we're telling Protos to do the write call, the WRITE write call. Okay, and then read will do similar. It will just store CA in that same place, and then that will be a read. I just have this little idea here. I don't necessarily want to just repeat all this code for read, although it's not that much code. So I could perhaps do something like this. So that puts the file descriptor down there. And then I could load that. Okay. And then store this here. Request count low. Request count high. Okay. Just call that do read. And that actually can go here. Oh, well, I'll call it, maybe just call it do RW. Okay, so for read, what I'm going to do is I'm just going to store the file descriptor in this temporary place, command block +6. Then I'm going to load CA, which is the read command, and then just branch to do RW, which of course this will always branch because it says branch if not equal to 0, and this is not equal to 0. So we'll go in here, we'll store that CA in the command byte down below. It will then store the request count and jump to do the reading and writing, or reading in that case. If you want to write, then you'll repeat this part. You have to store this first so that A is available to load this in, and then store it, and so on. So I've combined read and write into basically one little thing, and I put the command in the command block here so that it's there. I don't have to worry about anything. I mean, down here, it will just be there right here. I'm putting it right here so that this should do the right thing. Okay. Now, the thing is that this buffer, now this previous buffer that we had for the open command, wherever that is here, this buffer is a 1 kilobyte buffer that's just used internally by Protos to, keep data from the file. I actually believe half of it is for the current block that's been read out of the file from disk, and the other half of it is a block of like the directory or something, or it's like a block that points to other blocks. It's it's kind of bookkeeping information about it. Okay, and like I said, this has to be in memory, which is considered to be free by Protos. Well, down here in the read, this also has to be, and the write, this also has to be. I mean, the write actually is more important. Not the read isn't more important. This also has to be by memory, which is considered free by Protos, which to me just doesn't really make sense. I mean, like, it's my program, my memory. Why does Protos have to think it's considered free? Why can't I just why can't I just go down here and right here and say, suppose I want to read or write 32 bytes from the file. Why can't I just go down here and say, my buff 32? But if I do that, Protos will throw an error. If I try to read into this buffer, I try to read 32 bytes into this buffer here, it'll throw an error and say that I can't write the data read from the file to this buffer because, it's not accessible. It's not free, but it's my buffer in my program. Like, I understand why the 1 kilobyte IO buffer has to be in free memory, but I really don't understand why this one has to be in memory that Protos considers free. I think it's a big pain in the butt and basically a mistake. But nonetheless, that's the way it seems to work. So what I'm going to do here is I'm just going to go to the end of my file here. Okay, and what I'm going to do is there's let's see, an assembler directive here that we can use, a line 256, that will force us to go to the next page of memory. And now I've said page several times. What I mean by page is a 256 byte section of memory. That's what Protos considers a page for its purposes of memory allocation. So I can use this align 256 directive here. Okay, I can just say align 256. All right, and then this, what we'll do is just insert as many zeros as necessary to make sure that after this directive, we're at a 256 byte boundary. Okay, and here I will put my buff. And I'm not going to actually allocate anything because then that would be considered used. Instead, I'm just going to make an assembler no-op. So I'm just recording the address, right? So line 256, make sure that this label is at a 256 byte boundary. And I'm not going to, it's just basically on an empty line, but this label now has the address of this 256 byte boundary, which is after the end of my program. Okay, so I'll just call it my buff, and you know, if I go back up to the top now, I should be able to use that for reading and writing. Now I do want to have something to write, so let me so if I want to write something to the file, let's say I want to write, this is a test. Okay, I want to write that to the file. Null terminated. Here, I'm just going to call it tstir instead of teststir. All right, and etstir. Good. Okay, so first I'm going to try to write this to the file, and then I want to try to read it back out. That's my goal here. Okay, so here's where I close it. So I have to, I open it here. Okay, that's open. Here, let me make this a little bit easier to see here. Let's close. Unlink. Okay. Now I need the file descriptor. And X and Y, I'll have the name of my buffer, which was, I think, my buff. Just to make sure, yeah, there it is, my buff. There. Let's create. Okay, how much do I want to read or write? That's going to be the length of this thing here. So etstir minus tstir. And I have had some weird problems with this assembler when playing around with it and trying to get used to it, with it not recognizing it, having trouble with this stuff. Like I would expect I could do something like this. The length LT stir, the length of T stir is ET stir minus T stir. Now this seems to me like this ought to work always. But I've had problems with this thing saying expression too complex. Right here, let's just try it. Oh, operand value. Well, that's a different problem there, okay? Operand value not allowed. All right, let's go back to this here. Oh, it looks like it has to be outside of a segment. Okay. I'm just making sure there's nothing else that I was thinking of. I'm pretty sure that align directive is the one I want though, but okay. Yeah, I'm actually kind of yeah, I mean I know how I would do this if I thought the assembler could handle it, but I've had like I said, when I was playing with this assembler, I had some trouble with this thing and not really being able to do what I want to do. Well, okay, well I can do like this. Look, I had some trouble with it, you know, like trying to make expressions that would allow me to insert the right number of bytes that I want to insert and stuff like that. When my assembler is finished, it will not have these problems, of course. That's what we always say, right? Anyway, I could just call this start, right? I'm just making another little code segment here called myBuff, and of course it's completely empty, but it has that just this address of myBuff is going to be where I want it to be, which is the end of this line 256. Okay, so let's try that. Okay. Well, the funny thing is it looks like it accepted that little expression I had, although I had problems in the past with things like that, but well, yeah, it has an unresolved reference. That's no surprise because I haven't finished writing the code. All right, I can go ahead and put these things down here. Well, I didn't mean to do that. Okay, so I have those things there. Okay, I'm gonna write the string, put myBuff. Let me just go ahead and finish this here, JSR write. And now I need I'm sorry, what I'm gonna put here is the count, not the buffer. X and Y do not have the pointer to the buffer, they have the count. And like I said, I've had trouble with this thing. Like I would think I could put ltest there. Like ltest is equal to this minus this, which should be the length of the string. So let's try it. Like I've had trouble with this kind of thing, but if it works, I'll be happy. Okay. myBuff. Okay, and then JSR result. Is that what it was, right? Yeah. So I load the file descriptor. I load the length of the message I want to write to the file, the length of the data I want to write to the file into X and Y. I call write, and I have this pointer to my buffer that I want it to write from. It'll acquire the data to write from this buffer, right into the file, and then I say, did it work or not? Now, I'm not actually ready to test it right now. I mean, I guess I could, right? I just really want to see, does it assemble? It did. Okay, well, whatever problems I had before didn't crop up just now, and that makes me happy. So let's go ahead and try to run it. Okay, it writes at error 40. Okay, and so we have to go back to this here and see what the error is. Right? I don't see an error 40 there. That's not so cool. Of course, there could be some screw up in my code. It's definitely possible. There's a big thing on errors here. Invalid path name syntax is error 40. That seems extremely unlikely. All right, here we are. So let's go look at the code and see if there's something screwed up there. Okay, I put that out. I load my file descriptor. I load the length of the data that I want to write. Oh, okay, here's a dumb thing. Actually, I don't want to write from my buff, which is that buffer down there. That's for reading. I want to write tstir. I mean, this is not the kind of thing that should cause it to fail. Just, I wouldn't think so. I want it to write from there, from tstir into the file. Okay. Now, what happens, just to make sure, when I go to write down here, it's going to store that file descriptor, load cb into the command, and cb is the correct command for write. It's going to store the request count in 4 and 5, which is the correct place for it. Then it's going to jump to iPointer, which is going to extract that pointer. In this case, it'll be the address of tstir. And it'll end up down here. And it'll say compare. It's loaded the command block plus 0, that is the parameter count. If it's equal to 4, then it'll move 2 to 3, 1 to 2, and then 6 to 1. So this gets moved here, this gets moved here, and this, which is the file descriptor, gets moved up there. Then it will call the protos MLI, which should actually perform the write. Okay. All right. Still says error 40. Now that's very weird. It's, I don't know, really making me wonder if I'm ending up in the right place. Oh, you know what? I never stored that 4 in there, the parameter count. So yeah, clearly that's why it's not working. Okay. I can do that right here. There. Now I've stored the parameter count correctly. And if I could remember the name of my own program, that would be nice. Okay, and now it says it succeeded writing, and then it closed and deleted it, so the file isn't there. Right, the file called my file is not there. But it says it succeeded. Okay, and then we're going to want to read it back out. Oh, I'm looking at the wrong file. We're going to want to read it back out. Here's the write. Okay. After writing it, we want to read it back out. So here, all right, we'll print that. And I want to read out this many bytes. That is the length of the test. Okay. We need the file descriptor. Read. And now, where do I want to put this stuff I read? I want to put it into this myBuff, which is this stuff way down here, right? And remember, it's just down here, so it's like off the end of my program, so the page is counted as not being used. The memory is counted as not being used by ProDOS. Okay? I'll call that, again, in my opinion, like, doesn't make any sense, but whatever. Okay, and this is the read. But actually, we can't read this file unless we have to seek back to the beginning of the file, or we have to close the file and then reopen it. Otherwise, we're trying to read from the point we just finished writing, and there's nothing to read there, right? So when I create a file and then I open the new file I created and I write to it, the current location in the file is the end of what I just wrote. So if I try to read that, I'm not going to get anything. It's not going to work. So what I have to do is I need actually a seek call as well. I'm going to need to implement seek to have that work. And while I'm doing this, I'll just go ahead and insert that here like this. Okay, so put in seek, and seek is actually be quite similar to this one here, right? It's going to have the file descriptor. Let's just go look. Where is it? It's called a set mark or something like that. Here it is, set mark. So we need the file descriptor, the open file, and we need a 3-byte position in the file because ProDOS allows files to be up to 16 megabytes in size. So we need 3 bytes to say where we're going to seek to in the file. And I think what I'll do is it just makes sense to me to, because I don't have 3 bytes, like the file descriptor can be in A when you call, okay, seek. So we can put that in command block +1. So that's the file descriptor, right? But we don't have 3 bytes to store these things. We don't have, like 3 registers. We only have X and Y. So I think I'll just have the user push those on the stack. So we'll pull off the seek position off the stack. Now, of course, in the C language or Unix, seek has some options. You can seek from the beginning of the file, you can seek from your current position, you can seek from the end of the file and stuff like that. I'm just not going to bother with that at the moment. I'm just going to, you have to give it a position and you seek there. All right, so we're going to pull these off the stack and put them in bytes 2, 3, 4. Okay, like that. Prime count is 2. Have to store that. All right, and then we have the ProDOS call here. It is CE. call set mark, command block, and then just return, just like I did here for the close call. Okay. Now I could possibly, instead of just doing this all inline, I don't think it would really save much to do it as a yeah, like let's see, how would I do this? Like FD and pull A, store A, and command block minus minus FD would mean I store it in 0. So minus FEFF means I'm storing it in 1. Okay. And then increment X and branch if not equal to 0. Back to, I'll just call it loop for the moment. Okay, so what this would do is it would load X with FD, and when you want to store things in a place in memory using the X register as an index with and you want to go up, but you would like to not have to compare X to something. You just want to quit when it gets to 0 very easily like this. You can do it this way. Like I'm putting an FD in X, and then I'm saying command block. Actually, this is the wrong way, isn't it? DCB. This should be CB. Yeah. Command block minus FB. The reason for this is when I now add FD to FB, right? Basically, there. Let me just type it out here, right? Hex FD minus hex FB is 2. Okay? So I'm subtracting FB here, and I'm adding FD back in here. That's going to make it command block plus 2. Then I increment X, and X will be then FE, and that will then go into command block plus 3, and then X will be FF, which will go into command block plus 4, and then X will be 0, so it won't loop again, right? So that's how that works. But what does this do for me? I have here 1, 2, 3, 4, 5, 6, 7, 8, 9 bytes. Okay. Here I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's the same. It's the same number of bytes. There's no point in doing that. Okay, but I use that method actually quite a lot to store things into successive memory locations using the X register to index each successive byte, but not having to compare X to something to see if I'm done. Yeah, I just do it until X becomes 0, and then I'm done. All right, so we'll just do it like this. So you're going to pull the seek location off the stack. Low byte is always first. I mean, when you push it on, you push high byte, middle byte, low byte. When you pull it off, you pull the lowest byte, the middle byte, then the high byte, and store it here 2, 3, 4, as it says here, low, middle, high. And then the parameter count is 2. And we've already stored the file descriptor here and the reference number. Okay, and we call setMark. That looks like it should work. Okay, so what I want to do up here is just quickly, before I read, I'm going to want to seek. Okay, and I just made this skStir, skStir, put that out, Actually, at first I'm going to push this thing on the stack. So push, just push, push, push. That's putting a 0 on the stack because I want to seek to location 0. That is the beginning of the file. And I'll load the file descriptor, JSR seek, JSR result to print out the result of whether it worked or not. Okay. There's one more thing I'd like to do, but I'm going to go ahead and assemble and yeah, as I said, if I could just only remember the name of my own source file. Painful. Okay, there we go. Ooh, wonderful. I love a good crash in the morning. All right, let's see what happened here. We print that out, we load A, we push, push, push. Oh, okay. Well, that makes sense. Notice I'm pushing this stuff here, and then I'm doing a JSR to seek, right? I load the file descriptor, JSR to seek. So when I come down here to seek, what I'm actually pulling off the stack here is the return address, right? Not what I intended to pull off the stack, right? Which was what I intended to pull off the stack was the location I wanted to seek to, but what I actually pulled off the stack is the return address. And so that kind of sucks. Okay. Yeah, so what I'm going to actually have to do is I'm going to have to first pull off the return address. That will be the low byte of the return address. I'll put that in X. Pull off the high byte of the return address, put that in Y. Okay, now I'll pull off the pointer. I mean, not the pointer, but the offset, the seek location. And now I will push the return address back on the stack. Okay. Okay, so I create error 47. That's because it's already there. All right. Error 47 just means that the file already exists. That's because last time we crashed in the middle of it. If I run it again, now the file is not there because it was successfully deleted up above. It will now be all good. Okay, so everything says success. The very last thing I want to do before I'm done with this for today is I just like to print out that thing. I've read it back out. Let me print it out to prove that I've gotten it back out correctly, okay? And that should be quite easy. Okay, I'm going to go down here to read. All right, and again, I think what I'm going to do is, just like I did last time, I'm going to go ahead and push, like I did up above. I'm going to go ahead and push the processor status flag and then get it back here. And the reason for that is so if it failed, I won't try to print out, something from the buffer. I will only try to print out what was read if I actually succeeded in reading something. Okay? So I'll just call that, I'll say go to do close. It would be nice to write it correctly, close, okay. Now, if it did succeed, then I should be able to, it's read into my buff, and it's just it's an null terminated string. Oh boy. Okay, my buff, not moo buff. And then put a new line after that, because I didn't, well, you know what? How about I just put a new line down here? That way I don't have to worry about it. There we go. So it's going to write out, this is a test with a new line and a null byte, and then read it back in. And if it reads correctly, it will just print it out. Okay? Save it. Aha, I caught myself there. And try it out. That's nice, okay? That looks very nice. I've successfully created, successfully opened, successfully written, successfully seeked to the beginning of the file, successfully read from the file, printed out what I've read. This is a test. I successfully closed the file and successfully deleted the file. Good. So that is pretty much all I need as far as this file IO interface. What I've done is I've created an interface that is now independent of ProDOS. So if someone were to try to take this code and move it to another 6502-based processor, they would have to rewrite this file interface. But after having done that, then everything else should be good, right? Everything, the rest of the code from here on out, with just a few very small exceptions related to the memory map of the Apple II, is going to be processor independent. And it won't really matter which, I mean, not processor independent, but machine independent. It won't really matter which 6502 computer you run it on. As long as you have enough free memory to fit the assembler in and run it, then it should be fine. Okay, so now that I have this file interface done, I think next time the focus is going to be on actually starting to process command line arguments. That is, I'll look at the command line argument, open the file, and try to read characters from the file. And, you know, I guess what we're willing to work on is a scanner. We're going to have a scanner which will tokenize the input, and that the products of the scanner, the tokens that the scanner produces, will then be read by the parser, which will then actually, you know, parse the input, make sure everything's syntactically correct, and ultimately generate object code. So for the next time, it's going to be trying to begin on the scanner, and you know, prepare for actually looking at the source code, the assembly language source code, and doing something with it. All right, so that's it for now. So I will see you next time.